Hi guys, we're given a conservation of energy problem here and we're asked to answer a few questions below. The summary of this question is: a spring stretched 5 meters pushes a 95 kilogram skier down a slope 203 meters above the ground. The skier levels out and then goes down the remaining 99 meters. What is the skier's total energy at any point down the slope? What is the skier's velocity when they level out? And what is the skier's velocity at the bottom of the slope? Assume there is no friction in the system and all the energy is conserved. So the skier starts out 203 meters above the ground and is pushed by this red spring. The spring constant is K equals 9 newtons per meter, and the spring, remember, has been stretched 5 meters. As the skier goes down and levels out at this point where it's 99 meters above the ground, and then from there it just goes down and is at the bottom of the slope. Before we jump into this question, let's go ahead and look at the summary of the conservation of energy. A simple summary of this law states that the total amount of energy in an isolated system remains constant over time. The total energy is conserved. Since this is an isolated system, there's no external forces acting on this. There's no friction and no other forces externally. And since the total energy is conserved, going back to this diagram, we know that the total energy when the skier starts off will be the same amount of energy at this point, which will be the same amount of energy at this point, which will be the same amount of energy at this point, in this point. Although they're not the same types of energy, they'll be the same amount. And I'll explain that in just a bit. So now we have these important equations. The first one is U sub g, which is gravitational potential energy, equals mgh, where m is the mass of the skier, and g is the acceleration of gravity, and h is the height. Then we have U sub s, which is spring potential energy, which is 1/2 kx squared, where k is the spring constant and x is the distance the spring has been stretched. And then we also have k equals 1/2 mv squared, where k is kinetic energy and m is mass and v is the velocity. So let's go back to this diagram we began with, and let's figure out what type of energy the skier has and where. So as the skier starts off at point A, we know that the skier will have gravitational potential energy because the skier is 203 meters above the ground. And the skier will also have spring potential energy because the skier is getting pushed by this red spring. As the skier goes down and is at point B, or where it levels out, the skier now has gravitational potential energy still, but now also has kinetic energy. It has gravitational potential energy because the skier is 99 meters above the ground, and in order for the skier to get to point B, it went down this slope, which means it was in motion. So the skier was in motion, thus the energy from the spring has now been converted into kinetic energy at point B. What about when the skier goes down at the bottom of the slope and is at point C? At point C, all the energy is kinetic energy. All the energy that this skier began with at point A has been converted down the slope, and at the bottom of the slope has been converted all to kinetic energy since the skier is in full motion. For simplicity's sake, let's go ahead and figure out the total amount of energy at point A. And because of the law of conservation of energy, the energy at point A will be the same amount of energy at any point down the slope. The reason we pick point A to figure out the energy is because point B and C requires kinetic energy, and the equation for kinetic energy is 1/2 mv squared, which is where v is velocity, and we don't have the velocity, but we do have all the variables needed to solve for the energy at point A. So now let's go and solve for the energy at point A. At point A, or what's the skier's energy at point A? So remember, it's the combination of gravitational potential energy and spring potential energy. Setting up these equations for these two types of energy, we get E, or the total energy, equals mgh, which is gravitational potential energy, plus 1/2 kx squared, which is spring potential energy. Go ahead and replace these variables with numerical values. We get E equals mgh plus 1/2 kx squared, which is equal to 95 times 9.8 times 203, which is mgh, plus 1/2 times 9 times 5 squared, which is 1/2 kx x squared. Solving for this equation, we get the energy at point A equals 189,106 joules. So what's the sphere's energy at point A? Well, the sphere's energy at point A is 189,106 joules. So the sphere has 189,106 joules of energy at point A. And because of the law of conservation of energy, as I said earlier, the sphere has 189,106 joules of energy at any point down the slope, whether it's at point A, point B, point C, or any other point you can think of between here and here. Okay, well, when the sphere gets down to point B, what is the sphere's velocity when they level out, or when they get to point B? So remember, at point B, the sphere possesses both kinetic energy and gravitational potential energy, as mentioned earlier. So let's set up the equations for energy. Energy at point B would equal, let's go ahead and rephrase this. At point B, the sphere possesses both kinetic energy and gravitational energy, or gravitational potential energy. And the total energy at point B equals E equals mgh, which is gravitational potential energy, plus 1/2 mv squared, which is kinetic energy. And since we solve for E, or the amount of energy that the sphere has at any point down the slope, we have E equal to 189,106 joules. So since we have all the numbers we need, or all the variables we need for this equation besides V, we can actually go ahead and solve for V in this equation above. We can do that by subtracting mgh, multiplying by 2, dividing by m, and taking the square root. Doing so, we get V equals the square root of 2 times 189,106, which is the total energy, minus mgh over m. Go ahead and plug in the missing numerical values for these variables in this equation. We get V equals the square root of 2 times 189,106 minus 95 times 9.8 times 99, all over 95. Solving that equation, we get V equals 45.2 meters per second, which is very fast for a skier. No skier in the world should be going this fast. So it's a warning, don't ever do that. Okay, so the skier's velocity when leveling out is 45.2 meters per second. Okay, finally, what is the skier's velocity at the bottom of the slope, or at point C, when the skier is here? At the bottom of the slope, all the skier's energy is kinetic energy, as mentioned earlier. So setting the equation for energy, we get E equals 1/2 mv squared, since all the energy is kinetic, which equals 189,106, which is the total amount of energy at any point down this slope. Go ahead and solve for V, or velocity, in the equation above, and we get V equals the square root of 2 times 189,106 over m. Go ahead and fill in that missing variable, which in this case is only mass, and we get V equals the square root of 2 times 189,106 over 95, which equals 63.1 meters per second, which is even faster, which makes sense since at point C it's all kinetic energy, and at that point it'll have the maximum velocity. This is still very fast, and no skier in the world should be going this fast. Again, remember that. So at the bottom of the slope, the skier's velocity is 63.1 meters per second. Good job, we've answered all 3 questions. Good job.